Assalamualaikum. So today we're going to do a video presentation for Quadrature phase shift keying digital modulation. Beside me I have Tori, me Arshad, Adam and Wang.
Okay, for today's experiment, we're using Modicom board Modicom 31, Modicom 51, Modicom 52, and Modicom 32. Modicom 31 and Modicom 51 function as the transmitter, and Modicom 52 and Modicom 32 function as receiver. So we're using jumper wires to connect the connections and the power supply. So at the first board, function as transmitter, I measure the analog output here and the clock output at TP3 and digital output at TP44. So the graph is here. The yellow one is the digital analog output. The green one is the clock, and the blue one is the digital output. And also the AD converter we set to 0, 1, 0, 0, 0, 1, 1 as the input signal. So from the input we move to Modicom 51 board that undergoes through differential encoder bit that separate single data bit into two data bits, which is MSB and LSB, and it undergoes unipolar bipolar converters that reduce slight value of voltage. Then for the two signal undergoes first signal undergo modulator 1 and we measure at TP30 and TP33 for modulator 2, and the summing amplifier we measure at TP36 that acts as a QPSK signal. So the signal we have is here. The yellow one is the modulator 1 and the green is the modulator 2 signal. And for the summing amplifier we got the blue one, which is the QPSK signal. The output for modulator 1 is a PSK signal with phases of 0 and 180 degree, and the output of modulator 2 is a PSK signal with phase of 90 degree and 270 degree.
Okay, next the QPSK signal is transmitted to the Modicom 5/2 to be demodulated. So the signal is squared 2 times to obtain a sine wave at 4 times the frequency of the original QPSK carrier, but with no phase change. Then when there is no phase change, all phase change has been eliminated, the signal goes through the PLL block. The PLL, which is the phase lock loop, will lock on the incoming signal to produce a good clean square wave at the same frequency. And then the next stage is to divide the frequency of the PLL digital output by a factor of 4 so that the frequency is the same as the QPSK signal. So this is the waveform. As you can see, the yellow one is the signal after the PLL, and the green one is after it is divided by 4. The frequency is divided by 4. And the blue one is the signal that is in phase, while the red one is the signal that is in lagging phase. And then the two signal which is from the lagging phase and the in phase signal, which is the I and Q, is then transmitted to the low pass filter to be filtered. So the filtered signal is shown as in the yellow and the green signal. The next stage of the demodulation process is to square up the filtered signal in the data squaring circuit block through the comparator. So as you can see, the filtered signal has been squared up as in the blue and red signals shown.
And to complete the data squaring process, we sum it up at XNOR gate to produce the squared up wave and signal. And the wave or signal is the yellow one, which is squared up. So after the data squaring process, we pass it to the differential decoders block. We managed to take the clock input from Modicom 32 into this, and it decode to the debit decoder, and the debit decoder function as to look for any level changes in the 2-bit code at the comparator's output, and the wave or signal is the green one, which has been decoded. And from this, we transfer the signal to sync code detector, and we measure the output at TPM 43, and we also managed to capture the NRZ that is the daily version of the bit decoder. The yellow one is the output from sync code detector at Modicom 32, and the blue one is the delayed version of bit decoder at tipping from NRZ. So the input, so the AD converter for Modicom 31 is supposed to be the same as Modicom 32 at the DA converter, but we didn't manage to get the output because of some internal errors. And that's all from us. Thank you.